Good day everyone, my name is Shakrat Mohammed, student ID 20050448. As part of our CSE 47 on machine learning course here at BUET, I am pleased to present in-depth analysis of a landmark paper in our in machine learning field, deep residual learning for image recognition, the foundation of the ResNet architecture. The depth paradox. To understand ResNet, we must first look at the depth paradox. Before 2015, the consensus was simple: more layers equal more capacity, which should lead to better accuracy. However, the empirical reality was different. As networks reached a certain depth, performance began to drop rapidly. This wasn't just a plateau, it was a barrier where network depth became liability rather than a benefit. Unmasking the degradation problem. We call this the degradation problem. It is a common misconception that this is caused by overfitting, but our diagnostics prove otherwise. In a 56-layer plain network, the training error is actually higher than in a 20-layer network. Since batch normalization handles vanishing gradients, we conclude that the issue is a fundamental optimization difficulty. Current solvers struggle to find optimal parameters for very deep stacks of nonlinear layers. Okay, the core insight, residual learning. The author's breakthrough was to reformulate the learning objective in this paper. Instead of trying to fit a desired mapping h of x directly, we let the layers fit a residual mapping f of x. The final output becomes h of x equals to f of x plus x. The key takeaway is that it is mathematically much easier for an optimizer to learn a small perturbation toward 0 than to learn a perfect identity mapping from scratch. Okay. Next, the anatomy of basic residual block. So this is implemented through identity shortcut connections. As you can see in this diagram, the input x is carried forward and added to the output of the weight layers. This design is elegant because it introduces 0 extra parameters and adds no computational complexity. It allows standard solvers to train the entire network end to end without any modifications. Now, handling dimensionality, projection shortcuts actually. So one technical constraint is that the addition f of x plus x requires identical dimensions. When we need to change dimensions such as doubling channels or having the special size, we use a projection shortcut. This is executed as a 1-by-1 convolution, and here and this is executed as a 1-by-1 convolution to match the shapes. To remain economical, we only use this when strictly necessary, preferring the parameter free identity mapping elsewhere. So here the scaling up the bottleneck block To scale efficiently to extreme depths like ResNet 101 or 152, we use the bottleneck block. This uses 3-layer stack where on one by one convolution sandwich a 3 by 3 convolution. This reduces the channel dimension before the expensive 3 by 3 operation and restores them afterward. This allows the network to go deeper while keeping time complexity and model size similar to much shallower networks. Now, here is the comparison between plain versus residual networks. This is basically here this control comparison between a plain 34 and ResNet 34 network is revealing, and both have identical computational cost, 3.6 billion flops, and identical parameter counts. By keeping everything equal, the experiment isolates the skip connections as the sole cause for the ResNet converging successfully, while the plain net suffers from degradation. So here is the empirical proof solving degradation on ImageNet. The proof is in the results. The proof is in the results. On the left, you see the degradation problem in action. The 34 layer plain net has higher training error than the 18 layer net. On the right, ResNet, the situation reverses. The 34 layer ResNet demonstrates considerably lower error, definitely proving that depth has been unlocked as a usable design dimension. So here is the pushing the limits Cypher 10 experiments. On the Cypher 10 dataset, the authors pushed this limits even further. They trained 110 layer ResNet that achieved state-of-the-art results with only 1.7 million parameters. They even successfully optimized a 1202 layer model, while it eventually overfit due to the small dataset size. The training error remained below 0.1%, proving that the optimization barrier had been destroyed. Now, the 2015 clean sweep. This architectural wins lead to a total dominance of the 2015 competitions. ResNet achieved a 3.57% ensemble error on ImageNet classification. It also took first place in ImageNet detection, ImageNet localization, COCO detection, and COCO segmentation. It established a new gold standard for robustness across all computer vision tasks. Now, here synthesis, why residual learning actually works. While the original hypothesis focused on optimization, later research by Lee and others 2018 provided a visual proof. The lost landscape is craggy and chaotic, which traps gradients as visualized here. Skip connections dramatically smooth the lost landscape, creating a direct and smooth path for the optimizer to reach the global minimum. So, legacy, the universal standard actually, and finally the legacy of ResNet extends far beyond simple image recognition. The principle of residual learning has become a universal standard. It is a fundamental component in transformers for LLMs, units for medical imaging, diffusion models for generative AI. By solving the degradation problem, ResNet permanently changed the fundamental blueprint of deep learning. And it's all for today. Thank you.